Hi, we are now reaching the last block of Module 4, Ancillary Services, and this block will focus on the ancillary services themselves and related payments. For that, we're going to use Denmark as an illustrative test case, and Denmark is actually extremely interesting because originally Denmark is split into two parts, with the eastern part of Denmark, the power system there, being part of the Nordel power system for Scandinavia, and the western part being part of the continental Europe power system, which we commonly refer to as the UCTE system. This has implication in terms of ancillary services, their provisions, and related payments. For those interested, you may want to look at this document by clicking on this link in the related slides, and you will have an extensive description of ancillary services for both sides of Denmark, tender conditions, operational practice, etc. Today, there is a connection between those two sides of Denmark, but still we have different ways to refer to the ancillary services on the two sides of the link, and also there are different ways to consider contracts and settlement. For these two sides of Denmark, Western Denmark, DK1, and Eastern Denmark, DK2, let's focus on frequency-related services. In DK1, these are referred to as primary reserves, secondary reserve or load frequency control, as well as manual reserves or tertiary reserve. In contrast, in DK2, we talk about frequency control normal operation reserves, FNR, frequency control disturbance reserve, FDR, and manual reserve or tertiary reserves, which are the same as for DK1. We're going to look now at the case of DK1, since it will not add much more to focus extensively also on the case of DK2. Being part of a power system, like for the continental Europe, means that the whole power system has a single frequency. And this frequency there is of 50 Hz. When there are deviations from this ideal frequency, let's say, if the deviation stays small within the deadband, there is nothing to think about. But as the deviations actually get out of this deadband, then we need to act with primary reserve fast so as to support the recovery toward the frequency of 50 Hz. These primary reserve are sensing the frequency and acting automatically. They do not receive set points from the system operator. Since we have a single power system with a single frequency, we also have an overall need of primary reserve, which is estimated in Europe at 3,000 megawatts. It's estimated by the European Association of Transition System Operator, ENTSO-E. Based on this assessment, there is a recommendation for the various system operators within the area to contribute to their share of this 3,000 megawatts, and for DK1 this share is of plus minus 27 megawatts. I say plus minus since obviously this capacity may be used either to restore the frequency when it goes higher than 50 or to restore the frequency when it goes lower than 50. And then it relates to plus or minus regulation in practice. To provide primary reserve, one needs to first go through prior certification, which tells that your units can actually provide this primary reserve, and then you can enter this market. The certification for primary reserve in DK1 states that one should be able to deploy half of the committed capacity within 15 seconds and the whole committed capacity within 30 seconds. Then beside that, one should be able to hold this capacity for up to 15 minutes, which is the time scale we talk about with primary reserves. Then if you have the technical prior certification, you may enter the market. The market consists in daily day-ahead auctions, as we have for energy. We have on one side an inflexible demand, that this need of 27 megawatt that the system operator wants to procure for up and for down regulation. So we may have two auctions for upward and downward capacities. Looking at the supply side, we consider, as we did for energy, as for many auctions, we consider a merit order classification of the offers. So those that will offer the capacity for primary reserve at the lowest cost come first, and then it will be ranked with increasing price order. As for other auction mechanisms we've studied, for energy, for example, we have this clearing based on the meeting of the demand and the supply curve. At the point where they meet, we discover the clearing price that will be used for the settlement, and then all those offers on the left of this point, of this equilibrium point, those are the offers that are going to be scheduled, and on the right we have the offers that are not being scheduled. Remember that here we talk about capacity. Primary reserve being an energy neutral service, there will not be payment related to energy, only payment related to capacity. Let's look at an example here. Let's say that for a given time unit, say tomorrow for a given hour, we would like to procure primary reserves. 3 generators here are represented, G1, G2 and Z3, that offer some capacity for primary reserve. G1 with 10 megawatt at a price of 2 kroner per megawatt, G2 5 megawatt at a price of 5, and then G3 offers actually 6 megawatt at a price of 10 kroner per megawatt. And then there are some other generators that we do not represent. Based on a demand here that we set at 20 megawatt, we have the following clearing. The price, the clearing price, is going to be equal to the price of the marginal agent in the market, and that's G3. The price is of 10 kroner per megawatt. This price, if we follow uniform pricing, as we do in Denmark for primary reserve, is going to be the price that is received by all those that's going to be scheduled for primary reserve provision. So in this example, we have G1 that will be scheduled for 10 megawatts of primary reserve provision for a price of 10 kroner per megawatt. That leads to an overall revenue of 100 kroner. G2 is scheduled for 5 megawatts at a price of 10 kroner per megawatt. That's a revenue of 50 kroner. And finally, G3, that had offered 6 megawatt originally, is scheduled for only 5, so that's a revenue of 5 megawatt times 10 kroner per megawatt equal 50 kroner. Obviously, the others are not scheduled. They are on the right side of the equilibrium point. Here we only focus on generators, but actually for provision of primary reserve, the demand side could also be considered in the sense that batteries or electric boilers, for instance, can be very good at sensing the frequency and reacting very fast to support frequency restoration. Now we turn towards secondary reserves. Secondary reserves are there to relieve the primary reserve after they've been activated. Since we mentioned the timescales for primary reserves are up to 15 minutes. So after that, secondary reserve are taking over. This means in practice also some prior requirement is that this secondary reserve have to be able to pick up, you could say, within 15 minutes and then to hold afterwards. For DK1, we have a capacity requirement for secondary reserve of plus or minus megawatt of capacity, which is going to be procured in the way we'll describe in the next slide. For secondary reserve, since the timescales involved are a bit longer, and most likely it's going to be for events that requires more support in terms of frequency restoration, there will most likely be some energy involved. It's not an energy neutral service. Therefore, there will be a payment for capacity and also for energy. In terms of capacity, this is purchased on a monthly basis, so these are contracts for a certain period. The products are combined and symmetrical, upward and downward, so you have to be able to provide the secondary reserve in both ways up to the capacity agreed upon. And finally, these are bilateral contracts directly negotiated between the demand, which is Energinet in Denmark, the system operator, and then the outcomes and the conditions are not public, as is the case for bilateral contracts. As a result of this negotiation, a generator has a capacity committed or scheduled for secondary reserve provision, and then a price, which is a capacity payment per megawatt of secondary reserve provision agreed upon. Now, energy. All the energy that's going to be generated or consumed needs to be paid for if we look at a certain generator. To make this calculation, we need to consider two reference prices, the day-ahead price, lambda S, which comes from the clearing of the day-ahead market, as well as the balancing price, lambda B, that comes from the balancing market. Then the idea of the system operator to encourage provision of secondary reserve is that we need to have minimum revenues to be ensured, and this is done by always having a spread of at least 100 kroner between the day-ahead and the balancing price. In practice, that means for the upward regulation case, where you're going to get paid for the energy you somehow supply to the system, if the difference between the balancing price and the clearing of the day-ahead market price is less than 100, then the price that's going to be received for any energy supplied through secondary reserve provision, the price is going to be lambda S plus 100. But in the case that lambda B is at least 100 more than lambda S, then one directly gets lambda B times the energy that's supplied. On the other side, for the downward regulation case, one would have to pay back the system for the energy that is consumed through the provision of secondary reserve. To also support this process, somehow the system operator wants to ensure that this price is quite low, or at least you have a guarantee that the spread between lambda S, so the price at which you were paid to supply the energy, and the price at which you're going to have to pay back when you get this energy back through the secondary reserve provision, this difference should be at least also 100. So in the case where lambda B is greater than lambda S minus 100, so this spread is not insured, then the price to be paid back for the units of energy is lambda S minus 100. So you're guaranteed this 100 spread there. And if lambda B is lower than that, lambda S minus 100, then you directly get lambda B. We look at a basic example that permits to illustrate this mechanism. We focus on rogue trading, RT, and rogue trading is to generate 50 megawatt hours through the day-ahead markets. Lambda S, so the clearing price in the day-ahead market, is 200 kroner per megawatt hour. Rogue trading also has a contract for secondary reserve provision, and there the capacity committed is 10 megawatt, so that can be up or down, and the capacity price is 20 kroner per megawatt. In terms of illustrative cases, let's look first at upward regulation. Since it's fully committed, the energy is going to be fully delivered. 10 megawatt capacity times 1 hour is 10 megawatt hour. And the price from the balancing market is 250. Looking at the spread between the balancing and the day-ahead price, this spread is only 50 kroner. I told you in previous slide, we have to ensure at least 100 as a spread. So here, for the energy part, the price being received is 200 plus 100. So 200 being the day-ahead price, and 100 being this minimum spread that is guaranteed. The overall revenue eventually is composed by a capacity payment, 10 times 20, coming from the capacity reservation, and then 10 megawatt hour times 200 plus 100, which is the energy payment. Overall, this leads to 3,200 kroner in this case. In another case, through the usage of your capacity for secondary reserve provision, we could have that rogue trading is only delivering half of the energy that could be produced over this hour, so that's going to be 5 megawatt hour. The overall revenue in that case would be the capacity payment, as we had before, plus 5 megawatt hour times the price we should get for energy. This time, lambda B is more than 100 kroner higher than lambda S. It's 320 compared to 200. So we directly get the price lambda B for the energy payment. Combining the capacity and the energy payment, we get to 1,800 kroner. There is the other case that is relevant for downward regulation. Same starting point with 50 megawatt hour scheduled through the day-ahead market at a price of 200 kroner. There is the same contract for secondary reserve provision with capacity payment of 20 kroner per megawatt and capacity committed of 10 megawatts. In the first illustrative case, need for downward regulation, the energy is fully consumed, so the whole capacity is used to consume energy through the provision of secondary reserve, and the balancing price, lambda B, is of 150 kroner per megawatt. The spread here is at 50 kroner, while we should be ensured at least a spread of 100, so that when we pay back, the energy is at least 100 kroner cheaper than what we get paid for it. So in that case, the payment we receive for capacity is 10 times 20 for the capacity times the capacity price. And then we have to pay back 10 megawatt hour times this spread deduced from the 200 kroner of lambda S, so 200 minus 100. This is only for the secondary reserve provision, but remember that RT got a payment in the first place from the day-ahead market clearing, so this energy is actually some energy that you pay back from the original revenue you got from the day-ahead market. Here overall this leads to minus 800 kroner. In the downward regulation case that we have afterwards, we only consider that half of the energy is consumed through the provision of secondary reserve, and then the balancing price is of 50 kroner per megawatt hour. Same reasoning as before, we have this energy that is to be paid back, which is 5 megawatt hour, and then the spread here, 50 for lambda B compared to lambda S equal 200, this spread is at least 100, so we directly pay back this energy at the price lambda B. Overall, we have this capacity payment, and then we have to pay back this 5 megawatt hour at a price of 50 kroner per megawatt hour. This means an overall payment of 50 kroner. Remember that this is to be also combined with the original payment from the day-ahead market clearing. Finally, let's move on to tertiary reserve for the case of DK1. We have the full timeline here, and you see that these manual reserves or tertiary reserve, they come after the other in terms of timescales. And the requirement for manual reserves are also that one should be able to be at full capacity within 15 minutes. For this tertiary reserve, we have daily day-ahead auctions, same as for energy and primary reserve. We have a varying demand because the system operator is going to try to assess what is the uncertainty in the system and then look at what are the needs depending on the uncertainty. And this uncertainty can be dynamic. Some days the demand and the wind are uncertain, maybe some days they are not. Maybe some days you expect some outages, some other days you don't. So it's not like for the case of primary and secondary reserves where you had some set requirements. Here the requirements may vary depending on the weather and some other condition. The system operator needs to procure both upward and downward capacity, and we also follow a merit order on capacity offers. Eventually, energy is going to be paid for at the balancing price lambda B, since you're going to go through the regulation and balancing market to provide quantities of energy to help to keep the system into balance between supply and demand. Here is an example. Same example as before, where rogue trading is to generate 50 megawatt hours through the day-ahead market at a price lambda S of 200 kroner per megawatt hour. Rogue trading is cleared to provide tertiary reserve, and then the capacity payment is for a capacity of 20 megawatts at a price of 2 kroner per megawatt. Two illustrative cases for the upward regulation case. In the first case, the energy is fully delivered eventually at a balancing price of 250 kroner per megawatt hour. In that case, the revenue of rogue trading is 20 times 2 for the capacity payment plus 20 times 250. The overall revenue is 5,040 kroner. In another case, in the same need for upward regulation, maybe even though there's been this capacity reservation, only half of the energy is delivered, and let's say the balancing price is lambda B 320 kroner per megawatt hour. In that case, we still have a full capacity payment since these 20 megawatt were reserved, but eventually the energy delivered is only 10 megawatt hour times lambda B. That's an overall revenue of 3,240 kroner. On the other side, for downward regulation, with the same starting point, we look at the first illustrative case where energy is fully consumed, so you use the full capacity over the time unit at a balancing price of 150 kroner per megawatt hour. You would have this capacity payment again, and then you would have somehow to pay back this energy that you consume somehow by reducing your set points. So that would be 20 for the number of megawatt hours times 150 for lambda B. Eventually, this is a payment of 2,960 kroner, but you have to put this payment in perspective with the original revenue from the day-ahead electricity market. Finally, if we have a need for downward regulation, but the capacity is not fully used, so only half of the energy is consumed, you could say, and we have a balancing price of 50 kroner per megawatt hour, we will still get a capacity payment, and then we will have to pay back for these 10 megawatt hours that are being consumed at a price of 50 kroner per megawatt hour, and that means an overall payment of 460 kroner, still to be put into perspective with the revenue from the day-ahead market clearing. Thank you very much for listening. Now I would like to invite you to use the self-assessment quiz to check your understanding.